For number 8, trying to find the range and standard deviation, I'm going to copy that data, paste it in Excel. Now to find the range, we're looking for the difference between the largest and the smallest. With just 8 data values, you could probably do that by hand, but if you had 800 or 8,000, you'd want to use the formula. So you can find the minimum value out of all these, and then you can find the maximum value out of all these. And then your range would be just the difference between those two. So for our range, we're going to take C2 and minus C1 to find the difference between the largest and smallest value. And then for our standard deviation dot S for our sample, and then just select your data, and Excel will calculate the standard deviation of that data. And so remember, standard deviation, like range, is a measure of how spread out the data is. Number 9, you would do just like number 8 and figure out the range and the standard deviation. For number 10, refer to the beginning of this video to see how to use Excel to figure out the range and the standard deviation. But just like I did for number 8, you can copy the data into Excel and then figure out the range and standard deviation for both of those cities. What we're going to be doing then is comparing city A to city B and seeing which city has the biggest dispersion. The data is more spread out. And based on the range, for this example, city B is more dispersed because it has a higher range. There's a bigger gap between the lowest and the highest value. And then based on the standard deviation, again, city B is more dispersed because it has a larger standard deviation. The bigger the standard deviation, the more dispersed, the more spread out the data is. For number 11, we're looking at some random variables and seeing if they are discrete or continuous. To be discrete, the number of possible outcomes that variable could take on is going to be a countable number, and we can usually calculate it just by looking and counting. While with continuous, the number of outcomes the variable could take on are infinite, and we typically have to use some type of instrument to measure the actual value of the variable. So A says the number of fish caught during a fishing tournament. Now that's discrete. You would just look at someone's fishing bucket, and the only possibilities are 0 fish, 1 fish, 2 fish, etc. You can't have 2.5 fish or 1 1/3 fish. So you would just look and count. It's a discrete random variable. For B, the amount of snowfall, this is continuous. The snowfall can be any value 0 on up. It doesn't have to be a whole value like 0 inches or 1 inches or 2 inches. It can be anything in between. You can get 1.2 inches. You could get 3.47 inches. There's an infinite number of possible values you could get for the amount of snowfall, and you would have to use some type of measuring device to figure out exactly how much snowfall you had. For this distribution to be a discrete probability distribution, the possible outcomes here, their probabilities have to equal a total of 100%. So we're looking for the value to plug in here that would make all these values add up to 100%. And so what we need there would be a 0.29, and that would make them all add up to 1, which is 100%. For number 13, we have a histogram here, and it's looking at some mothers, and we're trying to see the probability of the number of children, the number of live births that they've had in their life. So what's the probability that a randomly selected mother has had her 4th live birth? So you would say has 4 live births. The probability is 0.114, and that's the answer. What's the probability that a randomly selected mother has had her 4th or 5th live birth? So now you need to add the probabilities of either being 4 live births or 5ths, add those two together to get the probability of being either 4 or 5. What's the probability that a randomly selected mother has had 6 or more live births? So now we need to add the probabilities for 6, 7, and 8, add all of those together to get the probability of having 6 or more live births. And D, I'm going to do in Excel, how many live births would you expect a mother to have had? And so I copied all the information into Excel here. You could have either 1 through 8 live births, and then the probability of each of those outcomes is listed here, and I just had to manually enter that from this histogram. There was no button to easily copy and paste. Once you get all that data, to find the expected value, you need to multiply the outcome, multiply it by the probability of that outcome, and you get a result. And then do that for each row. So this outcome multiplied by the probability of that outcome, and you get a result. And then you sum up all those results, and your sum here, this is the expected value. So for a mother giving birth, you would expect this to be her 3rd live birth. If you round that to the nearest 10th, it actually comes out to 3.0. Now another way to get to the same result that may be easier to wrap your head around why this is working, imagine there's 1,000 mothers, and if these are the probabilities of having either 1, 2, 3, etc. live births, then you would have this many mothers falling into each of the categories. So how many would have had 8 live births? Well, 0.042, which out of 1,000 mothers, that would be 42 mothers. How many have had 5 live births? 0.097. Well, out of 1,000 mothers, that's 97 mothers. So we have our group of 1,000 mothers. Here's how many fall into each category. Now let's look at how many total births they've had. You would get that by multiplying. You take the outcome multiplied by how many mothers fit into that category, and you get the total number of births. And then you do that for each of the categories. So out of the 42 mothers who have had 8 births, that comes out to 336 total births. And so now if we add all those up, we would have this many total births. Well, out of 1,000 mothers, let's do our average. This many total births divided by how many there are, you get your expected value, or your average number of births per person. Number 14 is an insurance situation. And here's the value the insurance company will pay out if the person dies. Here's how much the person has to pay in order to have that policy. And here's the probability that this given group of people, which for this example is a 19-year-old females, the probability they will actually survive. And so what we're looking for is the expected value of this policy to the insurance company. So from the insurance company's point of view, the probability the person lives is given, and the profit they'll make if the person lives is the $330 they paid to get the policy. The other option is the person dies, and the probability they die is right here. I figure that out by doing 1 minus the chances they live. So those two values have to add up to 1. A person either lives or dies. So 1 minus the chances of living gives you the probability of dying. And then what's the money look like from the insurance company's point of view? Well, they got $330 from the person, but then because the person died, they had to pay out $230,000. So 330 minus 230,000, this would be, from the insurance company's point of view, the value if the person dies. So to get the expected value for these insurance policies, you take the outcome and multiply it by the probability of that outcome, and then you do that for each of the outcomes. So multiply these two together. And when you sum those up for all the different outcomes, your sum here is the expected value from the insurance company's point of view. So what does that mean? It means that they expect for everyone who signs up, on average, that they're going to make $222.59 on every 19-year-old female that they insure.